Well, welcome to today's Safer World by Design webinar. And I'm very happy to have Katharina Brotzmann here, who's a postdoctoral research at the University of Heidelberg in Germany. And she's going to talk on a quite interesting and important topic in new approach methods. We're looking at the kind of quality of results you can get from zebrafish embryo testing. Of course, as a lot of you probably know, there's a lot of interesting mechanistic evidence possible to come from a test system like this. Katharina will talk for about 20 minutes, and then we'll just show a little bit and share for a couple of minutes how the data can be looked at by all of you. And then we'll take questions on the question box in the panel. You can also make questions. We usually have a very good discussion in this webinar, and we'll be happy to discuss, until the end. So with that, I hand over to you, Katharina. Looking forward to your talk.
Thank you very much, Barry, and thank you for the introduction. Hello, everybody. Thank you for the opportunity to talk to you and present part of my work, which was in collaboration with the UTOX Risk Project and our facilities for aquatic ecology and toxicology at the University of Heidelberg in Germany. And in the next couple of minutes, I want to show you some of my results for investigating the suitability of the zebrafish embryo as an alternative to mammalian teratogenicity tests. So let's get started. Now, okay. So in our daily life, we get contact with many different compounds, such as pesticides, herbicides, cosmetics, industrial chemicals, pharmaceuticals, food additives, just to mention a few. All of them have in common that before they actually get on the market and actually make contact with us, they have to survive several tests. One of them are teratogenicity tests, and usually those are performed in mammalian test systems like mice, rats, rabbits. But since there is the desire to reduce the amount of mammalian test systems more and more and find alternative systems, this is actually a pretty big issue in the last years. So the question is here, how can we reduce the amount of mammalian tests and make it maybe even a bit easier? One option could be, instead using of mammalian test systems, using something like fish, to be precise, the embryos of this fish. To investigate this, we have tested valproic acid and 9 of its analogues in the project and see how well the embryo is able to reproduce the adverse effects, which can also be observed in mice, for instance. So what's the point here? Valproic acid is a known anti-epileptic drug, and when it is consumed by pregnant women, it is known to raise the probability of neurotube defects like Hispina bifida. When it is consumed by mice, for instance, there are also neurotube defects, but the area is not down here, but more a cranial region. So the head is called exencephaly. Since neurotube defects are both in human and in mice in effect after application of valproic acid, we also focused in zebrafish embryos mainly on neurotoxicity for now. And we have two main questions here. The first one is the general toxicity, which is induced by instance valproic acid and its 9 analogues, even here comparable to the toxicity or the in vivo potential observed in mice? And based on those results, can we improve the comparability between mice and fish even a bit more, and how? Okay, so let's get started. General toxicity. Which test system are we using for this? We are using the fish embryo acute toxicity test, shortly FAT test. It is also fully described in the OECD Test Guideline 236, and basically it works like this. The day before you start your experiment, you put in a tank female and male fish, and the next morning they start to spawn. The eggs will be collected and immersed in the respective test solutions. Shortly after, all the eggs were selected for fertilized eggs, and those who were not fertilized or destroyed will be discarded. The fertilized eggs will be put in such 24 well plates, which were usually used in cell cultures, and those plates were pre-saturated for 24 hours to make sure that the substance, so the compound, doesn't stick to the wall of the plates, but actually gets in contact with the embryo itself. In each well, we put one embryo. Every 24 hours, we exchange the medium for freshly prepared medium, and we check all embryo individually for each effect and document them with photos, with videos, and by list per handwriting. This test can be done for 96 hours, and it can be extended to 120 hours post-fertilization, because fish embryos are regarded as a non-protected developmental state. So, according to the test guideline, there are 4 endpoints which are lethal. On the left side, you can hear the normal development of such embryos at 24 hours after fertilization or 48 hours. And lethal endpoints would look like this. We have here coagulation, no heartbeat, which can be seen here in the front, which is there's no pulse. And also when you look here at the back, there's no blood flow. Non-detachment of tail, which is here marked by the asterisk. Here should be the head. And also no somite formation, marked here by those arrows. But those are only the lethal endpoints. There are also a lot of sublethal endpoints, which can be caused by different compounds. For valproic acid, for instance, we have seen those. Here is a picture of a negative control at 120 hours, which is the latest time point we can get with this test system. And some of the effects which were observed for valproic acid look like this. We have a curved back, as well as a dark and not absorbed yolk sac. In comparison with the negative control, it is lighter in color. Here it's dark and bigger. A deformed heart, as well as deformed head and jaw, and edemata at the pericard, for instance, or at the yolk sac. Those are only a few of the endpoints you could actually see of these sublethal effects. And depending on the compound we have tested, there were in a single embryo between 10 to 28 different effects combined. According to the test guideline, all effects were combined into one graph, which looks like this. A short explanation here. On the left side, you see the percentage amount of affected embryos. Affected means here they have any kind of effect. And the time point is the latest point of the experiment, which is 120 hours post-fertilization. At the base, you see the substance concentration. And now you can see for each compound we have tested, there is one single curve. And when a curve gets up quickly, it means this compound is more toxic in the zebrafish embryo. So you can see for valproic acid, for instance, it is not the most toxic compound in the zebrafish embryo. It was actually 2-propyl heptanoic acid, an analog of it. And on the other hand, hexanoic acid was the least toxic compound in the fish. Now, if we stop here and take a look at this data and try to compare it with the in vivo potential data in mice, we can't actually say if any of those compounds are in vivo positive or negative in mice or human. because it really depends on the concentration you're using. At some point, all of them show effects. But what we can see here is that when we look at the 4 most toxic compounds in the zebrafish embryo, then we realize that those are also the 4 compounds which are in vivo positive in mice for neural tube defects. It is at least a hint, but there's still the question in the room, can we improve this? And sure, of course we can, at least we can try. Taking a step back, we see that each of those curves actually consists of all effects combined, all, for instance, 28 compounds in one, effects in one. But if we just select a few of those endpoints and start to compare them with the in vivo potency in mice again, maybe there is an improvement. So now is the question, which endpoints should it be? Ideally, we should have looked at something like an open head or an open spine, since this is a neural tube defect. Unfortunately, neural tube formation is different in mice and in fish. That's why we couldn't see any open head or open spine. So instead of that, we used or selected 3 other neurotoxic effects, which were actually observed in the embryo. I show you which those are. First of all, eye deformation, which has a direct connection to the neural system. On the left side, you can see here at 48 hours a normal developed embryo with a big black eye. It has 2 eyes, by the way, on each side. But on the right side, you can see here a treated embryo, which has a small eye, and also the pigmentation decreased drastically. The second endpoint is craniofacial deformation. Now, for all of you who don't really understand why is this a neurotoxic endpoint, let me explain. Neural tube defects in human and mice are strictly connected with the inhibition of histone V-acetylase, which is HDAC in short. Valproic acid is actually an HDAC inhibitor. And it doesn't actually not only inhibits HDAC in fish, in mice and human, but also in fish. Just the endpoint, the morphological endpoint of this inhibition looks differently in fish. In mice, we have a neural tube defect, but in fish, we have a deformation of the jaw. And this connection is also documented in 2 different AOP pathways. That's why this is the second endpoint. And the third endpoint, you can see here in this videos. On the left side, this is a normal fish at 120 hours. On the right side, you can see here, this is a treated embryo, and it can't keep up straight in the water. It always falls to one side. It twitches and shows tremor behavior. It can't really move properly. This is the third endpoint we have chosen. Now that we have selected all 3 endpoints, let's compare them to our in vivo potency in mice. And let's do this like this. We have here 8 different compounds, which actually also have in vivo potential data for mice. Plus means the effect was expressed. For mice, it was a neural tube defect, so exencephaly. And minus means there was no effect observed. If we now complete this table with zebrafish data in the same way, it looks like this for small eyes, for jitter tremor, and for craniofacial deformation. And if we compare it now, we can see that for 6 of 8 compounds, the trend of the zebrafish embryo actually follows quite well the trend of mice. Just for 2 compounds, there are contradictions. This means there is a concordance of roughly 75%, which is good, but maybe we can push it a little bit higher. When taking a closer look at the different model systems and the way how the compound is applied to them, there's one major difference. When a pharmaceutical like valproic acid is administered to mice, for instance, it is always buffered. In the zebrafish model, we usually don't buffer it if it stays in a specific pH range. We measure it, and if the range is fine, we don't change it. So now I thought, what might happen if I push back the pH to 7.75, so the ideal range for the zebrafish? I have repeated all those tests, and the result looks like this. And suddenly, we have a concordance of 100% with the mice data. So what does that mean now? Well, our questions were, is the general toxicity already good enough of the zebrafish to be compared with any potential in mice? And if not, can we improve it? And we saw, okay, when we only take the general toxicity in zebrafish, we can't actually say is this in vivo positive or negative, but we can say the most toxic compounds in fish are also the in vivo positive in mice. And we could improve this predictive power by selecting specific endpoints and by adjusting the pH of the test solutions. Now we have to keep in mind, this is only investigation for valproic acid and its analogues, and only for the endpoint neurotoxicity. What should be now the next step for that? To check if the embryo is a good opportunity and good option to be an alternative model for mice testings. Well, we should also look at other endpoints, at other substance classes, and be very careful in the choice of the specific endpoints. Those have to be a connection with the mode of actions which are connected to the specific substances we are investigating. And furthermore, just as a little tweak in all this, we have only looked at the zebrafish system from one specific test method, namely the acute in vivo toxicity test for embryos. But actually there is a whole row of more tests, which are all focusing on different endpoints, like stress behavior, endocrine effects, neurotoxicity, many other endpoints. Gene toxicity, metabolism, liver toxicity. All of them can be investigated and compared to mice and other mammalian data, and therefore also improved. Latest research also includes toxicokinetic data, which were also included in the UTOX risk project. I can't show it here now, but I have also the data there. So now in total, you can say the zebrafish embryo is a has high potential to be an alternative to mammalian test systems, but there are many points we still don't know. And those gaps in knowledge we can only fill if we investigate more different test systems in the zebrafish embryo, more different substances, and be very careful on what endpoints we are focusing on and how to correlate those with the endpoints observable in mammalian test systems like mice and ourselves. So at this point, thank you very much for your attention, and I'm really looking forward to your questions.